Hello, welcome to another video of thermodynamics. In this video, I'm going to explain how to find the properties of pure substances. First, let's see what a pure substance is. Pure substance is a substance that has a fixed chemical composition throughout the process. For example, we can consider water as a pure substance. At uh, at low temperatures, at low temperatures, water exists as ice. Its molecular structure is different, but its composition is still H2O. And then when you add heat, ice becomes water and it still has the same composition. And if you further add heat, water becomes steam, water vapor, that's still H2O. So this is some example of a pure substance. And throughout this course, we're gonna find the properties of water and another pure substance that we consider is R134A as a refrigerant. Let's look into what the phases are. Any substance can have different phases. There are three main phases that we encounter in physics: one is solids, liquids, and gases. In solids, uh, even though we don't need the thorough understanding of the molecular structure for the purpose of this course, we're gonna look at a little bit about the molecular structure here. In solids, molecules are arranged in a closed lattice, and the lattice has a definite shape. That's why the solid has that definite shape. And in terms of intermolecular attractions, solids has the strongest intermolecular forces. The molecules are attached to each other strongly, and they can be generally considered as these molecules stays in the same place. However, they constantly vibrate in moving around that equilibrium point. Liquids, on the other hand, has less intermolecular attraction than solids do. And also the liquid particles or the molecules are free to move around the neighboring molecules. That's why liquids gets that property of flow, and liquids doesn't have a definite shape. Liquids can get the shape of the container that it holds. And then gases has the least intermolecular attractions between the molecules, and the gas molecules are freely moving here and there. They have intermolecular collisions sometimes. So that's about solids, liquids, and gases. And whenever a phase change takes place, um, the temperature of the substance does not increase if the pressure is a constant. Now, in this case, you would see a situation where actually we use this concept of phase changing. And here what is elaborated is a fixed amount of water, fixed mass of water is heated gradually. At first, shows you that the water is at 20 degrees Celsius and 1 atm. It's called subcooled liquid or compressed liquid at state 1. And then slowly heat is added until the water gets into the saturated liquid state. Saturated liquid state is a state where water cannot um, absorb any more heat without converting it to a vapor. So as soon as it passes that state, saturated liquid, it immediately start converting some of part of the water into a, a gas or vapor, and then the liquid and vapor states or vapor components of that water stays in equilibrium uh, for some time. So in that state is called saturated liquid vapor mixture region. So once you pass state 2 where it is a saturated liquid, we have a saturated liquid vapor mixture state. So state 3 can be in between state 2 and 4 on this line. And one other important thing that you may notice is that at a constant pressure, the temperature at the uh, during the phase change process. Now, in this is called a phase change process because now the liquid phase is converted to steam phase or the vapor phase in this region. So as soon as it reaches it, as soon as all the water liquid is converted to steam, that is called another saturated state, saturated vapor state. So it's a saturated vapor, and then uh, uh, after that, the temperature starts rising again, which is called superheated vapor. And along this green line, the pressure is always 1 atmosphere. Pressure is called constant. So state 5 is a superheated vapor. State 4 is a saturated vapor. State 3 is a saturated liquid mixture, vapor mixture region. And state 2 is a, a saturated liquid region. Now, we can do this activity for different pressures. Here it has zero point 0.01 megapascal, that means 10 kilopascal. This is 0.1 megapascal, that's 100 kilopascal, close to 1 atmosphere. And 1 megapascal, 8 megapascal, 15 megapascal. And corresponds to all these different pressures, we have a uh, saturated liquid state, which I mark by that red dot. And we have a saturated vapor state here. Now, if I do the test for infinitely many number of pressure values, I can connect these dots and draw a continuous line. And this line is called saturated li liquid line. And at the critical point, it turns back again and goes through the saturated vapor line. So this line is called saturated vapor, this line. All the points on this line is a saturated vapor, is at saturated vapor state. All the points on this line at the left hand side are at the saturated liquid state. And based on that, this red curve is called the vapor dome or vapor envelope. And if we divide this into 3 different regions, this is a compressed liquid region, this is saturated vapor uh, liquid mixture region, and this is a superheated region. There are 3 regions. This is compressed liquid, two is saturated mixture. 3 is superheated vapor region. And that is how these envelopes are created for this diagram. This is a PV diagram, and this is also TV diagram. You can do the same. And you can see PV diagram for the constant pressure. You draw this dotted line, P1. When you have a greater pressure, it goes above the uh, previous line. And if you have a lower pressure, that goes below that P1 line. So if you want to draw constant temperature lines, it's going to be a horizontal line, constant volume line. Those are vertical lines. This is constant temperature. This is constant volume. And the next one that you see on your right is a PV diagram, same thing. Since your constant pressure lines are horizontal here, you get a constant temperature line that comes down and then stays straight and going down. And you have a higher temperature that goes above the existing one and lower temperature below the existing one. Here these are P constant, and you can also have a V constant line as well. Right. Now, how do we decide the region of the state? In each case, we have 4 different cases. Here we need the knowledge of reading tables. First of all, what I would do is my best practice is to draw for each case. I draw a small TV diagram or PV diagram. I like to draw TV diagram. And as soon as you draw it, you need to have that vapor dome for phase changing substances. And we have 50 degrees Celsius and 7.72 cubic meters per kilogram value. Let's look at our tables here. 50 degree, I would go to temperature table. Here you can see that table A4 is saturated water temperature. A4 has a second page. A5 is saturated water pressure table. Whenever you're not given the temperature, you are given the pressure, you can come into this table and look at further values. And then we have superheated water table. You can see that superheated water table is categorized as the value of pressure. Now what we're going to look at is the temperature table, because we have temperature given and it's 50 degrees Celsius. So this is the line that corresponds to 50 degrees Celsius. 50 degree correspondent is this. And we have volume, right? So we have 50 degree line, and then we're going to look at the pressure. Saturated pressure is 12.352. Psat at is given. Saturated pressure is 12.352. 12.352. So that's what we need. Hold on, I have to wait to decide that. How do I decide that? You are given the volume is, now we didn't actually pinpoint the state yet. So we have this 50 degrees Celsius constant temperature here. 50 degrees Celsius. And now we're looking for the value of V. At saturation at 50 degrees Celsius, you can see that this is belongs to saturated liquid. So saturated liquid value of volume is given as Vf. Saturated vapor value of the volume is given Vg. So then you look at the table. So what is the Vf and Vd? What are the Vf and Vg? Vf here is 0.001012, 12.026 Vf. So we have Vf is equal to 0.000 I don't remember, 0.00012 0010 001012, and Vg is this. This were taken at 12.026. 12.026. 12.026. Now look at the given value. The given value, because volume is increasing to this side, given value is higher than 0.0012 and it's lower than 12.026. So 7 point something should be here, right? So at 50, at this volume, this is the state, right? So this is in the mixture region. Mixture region. And you have pressure, we found that 12.352 because we know that it's in the saturated region. And this is how we find the state, where the state is at. If you have further questions, please don't hesitate to ask. So the next up, we have 400 degree cells, 400 kilopascal and saturated vapor thing. This is T V. Now we're gonna draw our little envelope. And given pressure is 400. I'm going back to 400 pressure table. Going back to the pressure table. And you see that let me stop sharing and then reshare it. Okay, back in again. So we have these values 12.06, and then we have pressure is 12.3352 for the 50 case, and then we were looking at 400 degree 400 kilopascal. So I'm going to pressure table. So this is a pressure table. At 400 is this. I underline that data row. And we asked to find the temperature. So we do not know what the temperature is because it's given only 400 degrees Celsius, and one valuable information was given there, that's called saturated vapor line. So I draw that small pressure line. This line corresponds to P equals 400 kPa, and right here is the saturated vapor. So you have given that it is here. So we can pinpoint that point because state, because we are given two different information. Saturated vapor says saturated vapor is saturated vapor line, and then 400 kPa pressure. So now it's at, this is Vg, right? Vg, and the temperature is the saturated temperature at 400 kPa, because the temperature does not change. You see, then the phase change process, the temperature doesn't change. So temperature is the same. So saturated temperature at the given pressure is 143.61. So we have 143.61. So this temperature is 143.61. And the next one up is 250 degrees Celsius and 500 kPa. I would first go to the pressure table because I found that is easier than to looking at the temperature table. So now I can draw that envelope. Again on a PV diagram. So, sorry, TV diagram. I can draw the constant pressure line, which corresponds to 500 degrees Celsius. This is P equals 500 kPa. And it says 250 degrees Celsius. Now this should be straight line, okay? And first thing that we need to find is what the saturated temperature is. So to find the saturated temperature at 400 K, go back to the pressure table. Saturation temperature is 143.61. So we 143.61. So this is 143.61. 4361. Okay. Here the temperature is 14361. Now the given temperature is above that. This is 250. So we can draw the given temperature line 250, and it meets the pressure line up here. So that is the state. This is a superheated state. So we figured that the state is at in this area, this region, that is called superheated. So phase region is superheated. To find the superheated properties, we need to go to superheated table. So saturated superheated table, table A6, superheated table. And the pressure is 500 kilopascal. 500 kilopascal is zero 0.5 megapascal at 250 degree Celsius. This is the data line. And the volume is, specific volume is 0.47443. 0.47443. So we have this value 0.47443. Uh, Now, in the previous case, we didn't look at the VG, V of G, VG value that is at 400 kilopascal and saturated vapor. VG, this go back to pressure, saturated water, pressure table, 400, and VG is 0.46242. 0.46242. And the last one is 350 kilopascal and 110 degrees Celsius. So we're going to draw again our small TV diagram. I'm drawing TV diagram. I suggest you draw this TV diagram for cases until you get used to this. And also TV diagrams and PV diagrams or TS diagrams are important in all the problems. I always want you to draw some kind of property diagram for any problem. So at 350 kPa, I draw roughly 350 kilopascal pressure line, constant pressure line, 350 kilopascal. And look at the saturated pressure at that pressure, saturated temperature at that pressure. So go to pressure table, 350 is here. Saturated pressure, saturated temperature is 138.86. So 138.86, 138.86 Celsius. And the given temperature is 110. So the given temperature is 110. It's below that line. So our state is right here. It's a compressed liquid. Compressed liquid region. Compressed liquid region. So to find the compressed liquid properties, we can either use compressed liquid table or we can approximate. Now, how to approximate is we can approximate the value of V here. V is equal to Vf at T given at compressed liquid region. We can assume that. So that is Vf at T given. T given is 110. So you go back to the temperature table. Go back to temperature table. 110 T P is 143.38. And VF is 0.001052, 0.001052. So you can fill that out, 0.001052. I hope that it makes sense. So the key is that you draw that little TV diagram for each case, and then you can find the properties from the table and mark it down on the diagram, and then you can find out the region that any state belongs to, and then you can read the other properties. So in the mixer region, to find the properties of the mixer region, you need a special treatment, that a special property that's called quality. You may already know because you already covered thermo 1. So quality is if you have that mixture of vapor and liquid together in the equilibrium state, this is vapor, this is liquid. So if you take this is mass of vapor and this is mass of liquid, the quality is mass of vapor, mass of the total water, total mass of the water. So you have mv divided by ml plus mv. So at saturated liquid state, basically in this state, now one important question is why is quality important in this region? It is because, let's say I found that this pressure is 100 kilopascal. let's say 100 kilopascal. And if you say that the temperature, we look at the table, 100 kilopascal, this 101.42. So temperature is 101.42. So if you are given that your system is at 100 degree kilopascal and 101.42 kilopascal temp Celsius, then we are in trouble because we cannot locate the point exactly. So we need one other property, that is the quality. So at saturated liquid, that means entire this container contains only liquid. So mv is 0. So we have x equal to 0. So at this state, x equal to 0. And then at saturated vapors, everything is converted to mv, and then ml is 0. So you have ml equal to 0, then x equal to mv divided by mv, which is equal to 1. So at here, x equal to 1. So if you want to find anything, any property in between that, we need to know what the x value is. And since we have Vf and Vg, right, we can find V for volume, Vf plus x times Vg minus Vf. And we can find Uf plus x times Ug minus Uf. And you can find H similarly, Hf plus x times Hg minus Hf. And Ug minus Uf and He minus Hf is given as UFG and HFG as well in the table. And S value can be found SF plus X times SG minus SF. And also this is given as SFG. So you can find SFG on the table, and that's how we find these values. So for any property, I can say that Y, for any property, YF plus X times YG minus YF. So you can say this is YFG. But this is not true for volume, because volume only has VG and VF. It doesn't have VFG value. I hope this makes sense. If you have further questions, please ask in the class. Now, when we go to superheated region, it's pretty simple. All you need is to figure out whether the given conditions are in the superheated region. So if you have TV diagram, what I can do is I can again draw that envelope, and what I would do is next find the pressure, given pressure, draw a constant pressure line. I mark it as P given, and then I look at the T set at P given, right? T set at P given, saturated pressure, temperature at given pressure. And this, if this is T given, that means T given is greater than T set at P given. So that's a superheated condition. And the other case scenario is that you have a condition that being in the superheated region is that your pressure, saturated pressure, is lower than the saturation pressure of the given temperature. For example, I can draw PV diagram. So PV diagram. You are given a temperature. So at the given temperature, I can draw. This is T given, right? And this is what? This is P set at T given, right? P set at T given. So if you have T given less than that T given, sorry, P given is less than P set at T given. So that means P given is less than P saturated at T given. That's the superheated region. Okay, that's a superheated region. And also, if you know what are the values of SG or UG and UF, let's say you know what is VG is at, and your V value is greater than VG, that's superheated, right? And it also, your S value is greater than SG, that's superheated. And the H value is greater than HG, that's superheated. U value is greater than UG, that is also superheated. So that's how you find whether it is superheated or not. But anyway, the idea is you draw that tiny TV diagram, or you use your original TV diagram that you draw for the problem, TV diagram or TS diagram, PV diagram. You can draw like that and mark the given pressure and then the saturated temperature, right? And then you can find the given temperature, and then you look at the state, and then find the other properties. And for the compressed liquid region, it's the same, so you draw the TV diagram or PV diagram, and then you draw the given pressure, and that's the saturated temperature at P given, and your T given is lower than T sat. This is T given at P given. Then you approximate this value. Let's say V is equal to VF at T given. H is HF at T given. S is SF at T given, right? For any property, you can approximate that, and also you can VU, UF at T given, right? You can find the compressed liquid, or you can use the compressed liquid table, which I don't advise a lot. So basically, that covers everything that I want to talk about. The properties of pure substances. The key is that you get an understanding of where your states belongs to, which region that state belongs to. Basically, we have 3 regions, like it is shown here, uh, and then using the tables, you can draw a sketch of, you can sketch PV or TV diagram or TS diagram, and then you can find where the state is at, where the state is at, and then from that we can find the properties referred to the correct table. Well, thank you very much for joining another video, and see you again. Bye.